Welcome to Summarize Science, where we break down complex research into ideas everyone can understand. Today, we are looking at a mathematical evolution of the classic game of cops and robbers played on graphs. In the standard game, a team of cops tries to land on the same spot as a robber while moving across a network of points and lines. Most people assume the players can choose to stay put, but researchers are interested in what happens when movement is mandatory. This led to the creation of sneaky active cops and robbers, a variant with two very specific and challenging rules. First, every piece must move to a new spot every single turn, meaning no one can ever hide in place. Second, the game is sneaky because the robber can actually move onto a space occupied by a cop without being captured. A capture only counts if the cop is the one who moves onto the robber's position during the cop's turn. The reason for these specific rules involves a concept called homotopy, which is a way of simplifying complex shapes into simpler ones. The researchers wanted a version of the game where the number of cops needed stays the same even if the graph is simplified or folded. They discovered that for graphs where every point is connected to itself, this new game behaves exactly like the traditional version. However, on other networks, the sneaky rules make the robber much harder to catch. For example, on a simple loop with an odd number of points, 2 cops are always enough to trap the robber. But if the loop has an even number of points, the robber has more room to maneuver, requiring 4 cops for a guaranteed win. The paper provides a helpful table showing how many cops are needed for different types of common mathematical structures. In a tree-shaped network, 2 cops are always sufficient to secure a victory. Things get even more interesting when combining 2 different networks together using mathematical products. The researchers found that whether a graph is bipartite, meaning it can be split into 2 distinct sets of points, changes the strategy entirely. To prove these theories, the paper uses visual diagrams to show every possible move a robber might make to evade capture. These chase diagrams help mathematicians visualize the logic behind winning strategies in multi-dimensional grids. To recap, this research introduces a new way to study networks by changing the fundamental rules of pursuit and evasion. By making the game sneaky and active, the researchers align the game with the mathematical theory of graph folding. This matters because it helps us understand how agents move through complex, changing systems. In the future, these rules could be applied to other types of mathematical theories or even digital geometry. Understanding these patterns is a key step in mastering the science of networks and connectivity. Thank you for watching Summarize Science, and stay curious about the hidden math all around us.